Hello, welcome to this first lesson on probability, where we're going to be looking at experimental probabilities with a bit of an investigation, okay? So let's jump right in. So, first of all, quite a big question. Can mathematicians predict the future? And I can say with 100% certainty that the answer is a solid maybe. Now, that's probably not the answer you were looking for, but the best we can do with maths is that we can calculate the probability that something happens. Probability. Probability, or sometimes we can use the word chance instead of it if you'd like, means how likely something is to happen. So if we were to take a timeline, for example, and at one end, we consider items that have a 0% chance of happening. On the other end, we consider items that have a 100% chance of happening. We can assign words to the parts of this timeline. So on the far left, something that has a 0% chance of happening can be called impossible. Something on the far right of the diagram can be certain it is guaranteed to happen. Now, what are some events? What some events could these be? Well, the sun rising tomorrow morning is an absolute certainty. If it doesn't happen, we've got bigger things to worry about. I'm quite likely to watch TV this evening, as you probably are as well. If I was to toss a coin, the chance that it would land on heads would be 50-50, because there's only two sides to a coin, and we're going to look at this later on in the lesson as well. Now, the chance of me finding a £10 note on the floor is pretty unlikely. You don't find £10 notes everywhere. So if you do find one, you've had a pretty lucky day. But it's very unlikely to do that. And the sun not setting tonight. Well, again, same as the sun rising tomorrow morning, is pretty. I can quietly say and confidently say that the sun will set tonight. And if it doesn't set tonight, we've got bigger things to worry about. So the sun not setting tonight is impossible. It is never going to happen. Okay. Why do we need probability? Well, from looking at a weather point of view, farmers use the weather to predict they need to know what the weather is most likely to be so they can plant their crops. And also around the world for extreme weather events like tsunamis and hurricanes, countries need to know if they're at risk from these weather events. Healthcare. So mainly this really applies to new medicines and treatments. We can only test so many treatments on so many people. If we then know that a new medicine works for 99% of people, we can only hope that it works for 99% of the whole population. So healthcare relies heavily on a probability of things working or not, because they can't test all new medicines on everyone, unfortunately. Business. So if you own a shop and you are looking to think about what things you want to stock in that shop, you want to stock things that have a high probability of selling, things that are highly likely to sell. And on the flip side, on a different version of business, if you want to invest your money and try and make lots of money, you want to invest your money in businesses that are going to give you a high return. If you make a wrong investment, you could potentially lose a lot of money. In politics, weeks and months leading up to elections, politics need to get as much information about what they think the voters will vote for on the day. So they need to get all sorts of statistics and numbers, all to help them figure out what they need to do to win this election. And in sport, if you're gambling or if you're playing sport, you want to know from a playing point of view, you want to know what is the best play you could do to win, how likely are you to score a goal. And from a gambling point of view, if you want to bet money on a team, you want to make sure you bet money on the team most likely to win. You don't want to bet on a losing team, otherwise there's no point. You can know you're going to lose money. So probability is used everywhere. It's a really common form of maths in the real world. So quick warm-up task. So we've got our probability timeline again, and we've also got an apparently random list of items here, and you need to put them on you need to put these on these timeline line here. How likely you think these events are, okay? Now, some of these are up for debate, and we'll chat about them when we go through the answers. But for now, pause the video and see which of these forms of likeliness apply to these statements. Okay, off you go. Okay, so if I was to organize these, so obviously starting from the left, pigs aren't going to fly. At least I hope they don't. That'd be interesting. Things that are unlikely, it will be hot tomorrow. Now, it doesn't matter when you're watching this video. I know we teach this video sometime in January, February. So it's usually cold then. So I think it's very unlikely it's going to be hot tomorrow. And it will snow on Christmas. It hasn't actually snowed on Christmas for a couple of years. It's pretty rare in the UK. So that's why I said unlikely. Rolling an even number on a dice, well, there's 3 even numbers and there's 3 odd numbers on a dice. There's 3 out of 6 options. There's only a half chance of getting an even number on a dice. That's going to be an equal chance. Likely now, I will pass my maths test. Anyone can pass a maths test if they do their revision, do their work. And it will rain today. Unfortunately, we live in Wales and it has been known to rain quite a lot. So that's why I put that there. And the sky will be blue. So the sky is always blue because of the oxygen in the atmosphere. If the sky isn't blue, we haven't got any oxygen. And again, we've got bigger things to worry about than the probability of the sky being blue. So those were my answers. I hope you got something fairly similar. So let's consider a coin toss, okay? So I know that if I throw a coin can only land on heads or tails. There's only 2 outcomes. Therefore, I can calculate a theoretical probability of a coin landing on heads. So the notation we use in statistics and maths is P of heads. And all that means is the probability of heads. And that is equal to a half. How did I get a half? Well, the top number is the number of successful outcomes. In this case, a successful outcome is the coin landing on heads. And the bottom number is the total number of outcomes. There's only 2 sides to a coin. So there's 1 successful outcome and there's 2 possible outcomes. So the probability of coin landing on heads is a half. Therefore, the theoretical probability of a coin landing on head is half, which we can change to a percentage to be 50%. I think we can all follow that. So I got a coin and I threw it 5 times in a row and I got the following: heads, heads, tails, heads, heads. So for 5 coin tosses, I got 4 heads and I got 1 tail. So this is called an experimental probability. So we get experimental probabilities when we actually carry out the experiment, so to speak. The top number, where I got 4 over 5 from, the top number is the number of successful outcomes, i.e. the number of times the coin landed on heads. The bottom number is the number of events. So because we tossed the coin 5 times, there were 5 events. We can now change 4 over 5 into a percentage, which is 80%. So if I throw a coin 5 times in a row, I get the following results: heads, heads, tails, heads, heads. So out of 5 coin tosses, the coin landed on head 4 times and it landed on tails once. That would give me an experimental probability of the coin landing on head of 4 out of 5. How did I get those numbers? Well, the top number was the number of successful outcomes. So how many times did the coin land on head? And the bottom number is the number of events. How many times did I throw the coin? And that comes out and that gives me a number of a probability of 80%. So going from these results, there is an 80% chance that if I throw the coin again, the coin will land on heads. Okay? But is that right? Let's have a little think about it. So, first question we need to ask about this is this a fair coin? So a probability of heads of 80% would certainly indicate that it's not a fair coin. After all, there's only 2 sides to a coin, and we're expecting, if we're asking the chance of one of them happening, that should be 50%. 80% is quite far away from 50%, so maybe we need to think about this as an unfair coin. Maybe it's weighted in a certain way. But can we make this big assessment on only 5 coin throws? So not really, because 5 is not enough. 5 data points is not enough to make something statistically significant, okay? We need to throw the coin a lot more times before we can say anything like this with confidence, okay? So what about throwing it 10 times, 50, 100, 1,000? What about 10,000, 100,000 times? Well, luckily for you, I did just that, so you didn't have to. And I'm going to show you the results now, okay? So the top of the table, I threw my coin 5 times, and it landed on heads 4 times. When I threw it 10 times, it landed on 6. 50 times, it landed on heads 24 times. When I threw it 100 times, it landed on heads 54 times. When it threw it 1,000 times, 518. And for 10,000 times, it landed on heads 4,981 times. Now, the last one, I'm going to keep it blank. That's going to be a surprise very soon. So I'm not going to tell you how many times it landed on heads when I threw the coin 100,000 times, okay? But What I've also figured out for you is the experimental probability for all of these throws, okay? And all I've done is just divide the amount of times the coin landed on heads by how many throws I had, how many throws I did. So have a little think to yourselves, what do you notice about the experimental probability as the number of throws increases? Pause the video and have a quick think. Okay, so hopefully you realized, or you've noticed, as the number of throws or the number of events increase, we're getting closer to that theoretical probability of 50%, that golden number, okay? Getting so close that we're actually 0.2% away at 10,000 throws, okay? Now that's a lot of throws, but that just shows that actually this coin was a fair when it is actually getting to 50% of the time it lands on heads. So what I've also done here is I've made you a nice little graph, okay? And this graph shows the probability of the coin landing on heads, the experimental probability, how that changes the more times we throw the coin. So you may have noticed this x-axis, it doesn't increase by one every time. It increases quite quickly as you go along it, okay? But the most important thing to look at is this the green dots here, that represent the 50% probability. So that is where that was where we would expect our experimental probability line to lie, okay? If we look at the orange line, which is the experimental probability, we can see that's quite high. And that's what we were saying before. We were saying there's quite a high chance of the coin landing on heads, first of all. But as we go along the graph, we can see that orange line gets close, it zigzags, it goes up and down, but it gets closer and closer to 50% until at roughly the 10,000 mark, it's basically 50%. So it took us about 10,000 throws to prove that this was a fair coin, okay? And that number won't change now. If you rolled the dice millions and billions and trillions of times, it would not deviate from that 50% mark, okay? So to answer one more question on this now, got a question in the box down here. If I was to throw a coin 100,000 times, which is this amount here, how many times would you expect it to land on heads? Well, remember, our theoretical probability was 50% or a half. So if I wanted to find how many times I'd expect a coin to land on heads, I'd have to do 100,000, which is the amount of times I've thrown the coin, and I'd times it by a half, because that's the chance of me getting heads or tails is a half, isn't it? So 100,000 times a half is 50,000. So that's how many times I would expect it to land on heads. So 50,000 times. Now let's have a look at how many times it actually did land on heads. 50,232. Now I know it's 232 off, but actually, when we're talking 50, throwing a coin 100,000 times, that's very, very close. That's only 0.2% off from our guess. Using probability, we guessed 50,000 and we're only 200 off. So that's incredibly close. Okay, so that's what probability does. It doesn't tell you exactly what it's going to be. It just gives you a really good estimate of what it should be or what it could be. Okay, let's do another example with a dice throw. So, dice throw. Now, I know if I roll a dice, it can only land on 1, 2, 3, 4, 5, or 6. Therefore, I can calculate the theoretical probability of a dice landing on the number 3. So, just to remind you guys, P of 3, that just means probability of rolling a 3 on a dice. And that is 1 over 6. How have I got that? Well, the top number is the number of successful outcomes. Again, there's only one number 3 on a 6-sided dice, so the number of successful outcomes is 1. And the 6 is the number of total outcomes, and there's 6 sides on a dice, so there's 6 different outcomes. And if we turn that 1 over 6 into a percentage, we get a theoretical probability of the dice landing on 3 of 16.67%. So I went away and I threw a dice 5 times in a row, and I got the following numbers: 6, 3, 6, 5, and 6. So to summarize, from 5 dice rolls, I had 1 3, 1 5, and 3 6s. That would give me an experimental probability of the dice landing on 3 of 1 over 5. How did I get that? Well, the number of successful outcomes, the dice only landed on 3 once, so that was the one successful outcome. And there were 5 different events. I rolled the dice 5 times. So the experimental probability is 1 over 5. Change that to a percentage, that's 20%. So compare that to our theoretical probability of 16.67%. Well, we're looking pretty close now. It's only 3% off, okay? That's pretty darn close for only throwing the dice 5 times. But again, is this a fair dice? So, like I said, a probability of rolling a 3, an experimental probability of 20% would indicate, yeah, that's pretty good. It's looking pretty good. It's relatively close to 16.67%. But again, we can't say this for certainty by only throwing the dice 5 times. So I got some dice and I threw these dice 10, 50, 100,000, 100,000 times purely for you guys. Aren't you a lucky bunch? And here's the numbers I got. So when I threw it 10 times, it only landed on 3 once more. Well, it didn't land on any more. It still landed only once. When I threw it 50 times, it landed on 3 7 times. When I threw it 100 times, 23 times. When I threw it 1,000 times, landed on it 181 times. And when I threw it 10,000 times, it landed on it 1,682 times. And again, the last one, I'm going to leave the number of threes thrown as blank, okay? But have a look at the experimental probability again. How does the experimental probability change as we increase the number of throws on the dice? And once again, as the number of throws increase, we're getting ever closer to that 16.67 theoretical probability, to the point where we are now 0.04% off. Okay, that's even closer than when we were throwing the coin. Okay. So again, I've made you a nice little graph showing you this now. So the green line represents the experimental probability of rolling a 3. And we can see that very early on, with only throwing the dice a couple of times, at first the chance of getting a 3 is quite high. But as we go across the numbers, as we throw the dice more and more times, the green line gets ever closer to that theoretical probability, which is the black dotted line. And the same as the coins, around about 10,000 times, that is when it started to line up with the theoretical probability of 50%. All right. So one last question on this now. If I was to throw a dice 100,000 times, how many times would you expect it to land on 3? So maybe you're going to pause the video if you want to have a go on this, okay? So just go through the answer quickly. So if I was to throw a dice 100,000 times, how many times would it land on a 3? Well, the chance of getting a 3, the probability of landing on 3 was 1/6. So over 1/6. And if you type that into your calculator, you should get, it'll be a decimal number, but we're going to round it to 16,667 times. Okay? Let's compare that to the actual number I got. 16,709. And that's even closer than the amount of times when we were throwing heads and tails on the coin. It's like 40 away. It's 30, I think it's 38 away. That's incredibly close. That's for landing 16,000 times to be 38 away. That's incredible. That's incredibly close, okay? So hopefully this shows you how it may not appear fair at first, but if you do it enough times, probability can pretty closely tell you how many times you can expect something to happen, okay? So as a quick summary, calculating the probability of an event will not tell you exactly how many times it will occur and when will it occur. It just won't do that. What it does, though, is it provides you with an indicator of how many times it should occur given any amount of throws, okay? And you can use those numbers to make educated guesses. So checking question now. If I roll a fair 6-sided dice 1,000 times, so I get a 6-sided dice and I roll it 1,000 times, how many times would you expect to get an even number? Okay, so pause the video, have a think, try figuring out the theoretical probability for this question. Okay, and this is just your first lesson on this, so don't worry if you get it, but see if you can figure out how many times you would expect to get an even number on a dice if you rolled it 1,000 times. So pause the video, have a quick go. Okay, so let's think about what is the chance of getting an even number. So what is the probability of an even number? Well, how many even number on a dice? So we've got 1, 2, 3, 4, 5, and 6. How many of those are even? Well, 2, 4, and 6. So we have 3 successful events, if you will, out of 1, 2, 3, 4, 5, 6. So it's a probability of 3/6 that we're going to get an even number when we roll a dice. We can simplify 3/6 as a fraction to 1/2, and we can turn a half into a percentage of 50%. So now we know the probability, the theoretical probability of getting an even number is 50%. Therefore, if we rolled the dice 1,000 times, 1,000 multiplied by a half, because that's how often we'd expect to get an even number, that gives you 500. So we'd expect to land on an even number 500 times. So very well done if you figured that out. But hey, let's see how close we actually were. So I told a bit of a fib. I didn't actually roll the dice and throw the coin hundreds of thousands of times. I used a website, okay, to give me the answer. So, or to virtually roll hundreds of thousands of dice for me, okay? So let's have a look at so if we look at the data now, so what this basically tells us, it's a bit much going on. But what this told me, let's check our answer compared to our estimate of getting a number 500 times. Well, I can see here that the machine rolled a 2 172 times, it rolled a 4 154 times, and it rolled a 6 188 times. So let's add those numbers up. These are technically real world numbers, okay? So we've got 172 plus 154 plus 188. And if you add all those numbers up, you would get 514. So just to put that into perspective, we estimated that it would land on an even number 500 times, and the actual was 514 times. Now, basically, that's pretty incredible. If you were to guess within 14 of 1,000 events, then you've done very well there. But that just shows how powerful probability can be. Okay, so in this case, we're messing around with dice and coins, but in the real world, you could be potentially investing investing millions of pounds. Okay, and if you do your maths right, you could come up big bucks. Okay, so this is really useful maths. Okay, really good maths. Hey, thank you for the lesson. Thank you for joining in. And the next lesson, we're going to start working out more probabilities using this. Okay, thanks for listening. Bye now.